When dealing with overcurrent protection for conductors, specifically after ampacity adjustments, it's crucial to understand how the National Electrical Code, or NEC, Section 240.4b applies. This section addresses the protection of conductors and states that the overcurrent protective device, or OCPD, must be selected based on the conductor's ampacity after any applicable adjustments have been made. Let's consider a scenario with 8 current-carrying conductors installed in a 1-inch conduit. The conductors are number 10 American wire gauge, or AUG, XHHW-2 copper. According to NEC Table 310.16, the 90°C column indicates that number 10 AWG copper conductors are typically rated for 40 amps. However, when multiple current-carrying conductors are bundled together in a conduit, their ampacity must be adjusted to account for the increased heat generated. NEC Table 310.15b3 provides adjustment factors for the number of current-carrying conductors in a raceway or cable. For 7 to 9 conductors, the adjustment factor is 70%. Therefore, the adjusted allowable ampacity for the number 10 AWG conductors in this scenario is 40 amps multiplied by 70%, which equals 28 amps. The question then becomes, does NEC Section 240.4b apply after the conductor's ampacity has been adjusted to 28 amps? The answer is yes. NEC Section 240.4b explicitly requires that the size of the overcurrent protective device be selected based on the ampacity of the conductor after any applicable adjustments have been made. In this case, the conductor's ampacity has been adjusted to 28 amps due to the number of conductors in the conduit. Therefore, the overcurrent protective device must be sized appropriately for 28 amps. However, it's essential to consider an additional limitation. The overcurrent protective device cannot be sized for more than 80% of the conductor's allowable ampacity as outlined in certain subsections of NEC 240.4. In this specific case, 80% of 28 amps is 22.4 amps. Therefore, the maximum size overcurrent protective device that can be installed is a 25 amp breaker, since standard overcurrent protection sizes do not include a 22.4 amp breaker. In summary, NEC Section 240.4b applies after the conductor's ampacity has been adjusted. The overcurrent protective device must be sized for 28 amps, which is the adjusted ampacity of the conductor. However, the overcurrent protective device cannot be sized for more than 80% of the conductor's allowable ampacity, resulting in a maximum overcurrent protective device size of 25 amps. To further clarify the application of NEC Section 240.4b, let's break down the key concepts involved. Firstly, conductor ampacity refers to the maximum current, in amps, that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. The ampacity of a conductor is determined by factors such as the conductor's size, material, insulation type, and the ambient temperature. NEC Table 310.16 provides ampacity ratings for various conductor types and sizes under specific conditions. Secondly, ampacity adjustment factors are used to account for situations where the conditions of use differ from those assumed in NEC Table 310.16. These factors adjust the conductor's ampacity to compensate for the effects of ambient temperature, the number of current-carrying conductors in a raceway or cable, and other factors that can affect the conductor's temperature. Thirdly, overcurrent protection is the process of protecting conductors and equipment from excessive current that could cause overheating, damage, or fire. Overcurrent protective devices, such as circuit breakers and fuses, are designed to interrupt the flow of current when it exceeds a predetermined level. NEC Section 240 provides detailed requirements for overcurrent protection. NEC Section 240.4b is a critical provision that addresses the relationship between conductor ampacity and overcurrent protection. It requires that the overcurrent protective device be sized to protect the conductor based on its adjusted ampacity. This means that after applying any applicable adjustment factors, the overcurrent protective device must not exceed the adjusted ampacity of the conductor. The 80% rule, which limits the overcurrent protective device to no more than 80% of the conductor's ampacity, is another important consideration. This rule is intended to provide an additional margin of safety and prevent nuisance tripping of the overcurrent protective device. It is important to note that the specific requirements for overcurrent protection can vary depending on the application and the type of equipment being protected. Therefore, it is essential to consult the NEC and other applicable standards to ensure that the overcurrent protection system is properly designed and installed. Let's consider another example to illustrate the application of NEC section 240.4b. Suppose we have 6 number 12 AWGTHN copper conductors installed in a conduit. According to NEC table 310.16, number 12 AWGTHN copper conductors are rated for 30 amps at 90 degrees Celsius. However, since there are 6 current-carrying conductors in the conduit, we must apply an adjustment factor from NEC table 310.15b3. For 4 to 6 conductors, the adjustment factor is 80%. Therefore, the adjusted allowable ampacity for the number 12 AWG conductors in the scenario is 30 amps multiplied by 80%, which equals 24 amps. According to NEC section 240.4b, the overcurrent protective device must be sized based on the adjusted ampacity of 24 amps. However, we must also consider the 80% rule. 80% of 24 amps is 19.2 amps. Therefore, the maximum size overcurrent protective device that can be installed is a 20 amp breaker, as standard overcurrent protection sizes do not include a 19.2 amp breaker. In this example, the 20 amp breaker will provide adequate overcurrent protection for the number 12 AWG conductors while also preventing nuisance tripping. It is important to note that the NEC permits the use of the next highest standard overcurrent protective device size in certain situations, such as when the calculated overcurrent protection requirement does not correspond to a standard size. However, this exception is subject to specific limitations and conditions, and it is essential to consult the NEC to determine whether it applies in a particular situation. In addition to NEC section 240.4b, other NEC sections may also be relevant to overcurrent protection. For example, NEC section 210 provides requirements for branch circuits, including the overcurrent protection of branch circuit conductors. NEC section 430 provides requirements for motor circuits, including the overcurrent protection of motor circuit conductors and motor overload protection. These sections provide specific requirements for overcurrent protection in different applications, and it is important to be familiar with them to ensure that the overcurrent protection system is properly designed and installed. In summary, NEC section 240.4b is a critical provision that governs the overcurrent protection of conductors. It requires that the overcurrent protective device be sized based on the adjusted ampacity of the conductor, taking into account any applicable adjustment factors and the 80% rule. By following these requirements, we can ensure that conductors are adequately protected from overcurrent and that the electrical system operates safely and reliably. To further expand on the topic, let's discuss the different types of overcurrent protective devices that are commonly used in electrical systems. The two main types of overcurrent protective devices are circuit breakers and fuses. Circuit breakers are electromechanical devices that automatically interrupt the flow of current when an overcurrent condition occurs. They typically consist of a bimetallic strip or a magnetic coil that is sensitive to current. When the current exceeds a predetermined level, the bimetallic strip bends or the magnetic coil trips, causing the circuit breaker to open and interrupt the flow of current. Circuit breakers can be reset after they have tripped, allowing the circuit to be restored to normal operation. Fuses, on the other hand, are one-time devices that interrupt the flow of current by melting a fusible link when an overcurrent condition occurs. The fusible link is a metal conductor that is designed to melt at a specific current level. When the current exceeds this level, the fusible link melts, opening the circuit and interrupting the flow of current. Fuses must be replaced after they have blown. Both circuit breakers and fuses are available in a variety of sizes and types to meet the needs of different applications. Circuit breakers are typically rated in amps and volts, and they are available in standard sizes ranging from 15 amps to several thousand amps. Fuses are also rated in amps and volts, and they are available in a wide range of sizes and types, including cartridge fuses, plug fuses, and blade fuses. When selecting an overcurrent protective device, it is important to consider the following factors. Firstly, the ampacity of the conductor being protected. The overcurrent protective device must be sized to protect the conductor based on its adjusted ampacity, as discussed earlier. Secondly, the interrupting rating of the overcurrent protective device. The interrupting rating is the maximum fault current that the overcurrent protective device can safely interrupt. It is important to select an overcurrent protective device with an interrupting rating that is sufficient for the available fault current at the point of installation. Thirdly, the voltage rating of the overcurrent protective device. The overcurrent protective device must be rated for the voltage of the circuit in which it is installed. Fourthly, the type of load being protected. Different types of loads, such as motors, transformers, and lighting, may require different types of overcurrent protection. For example, motors typically require overload protection in addition to overcurrent protection. Fifthly, the environmental conditions. The overcurrent protective device must be suitable for the environmental conditions in which it is installed, such as temperature, humidity, and corrosive atmospheres. By considering these factors, we can select an overcurrent protective device that will provide adequate protection for the conductors and equipment in the electrical system. In addition to selecting the correct size and type of overcurrent protective device, it is also important to ensure that it is properly installed and maintained. Overcurrent protective devices should be installed in readily accessible locations and should be protected from physical damage. They should also be regularly inspected and tested to ensure that they are functioning properly. Circuit breakers should be tested periodically to verify that they trip at the correct current level. Fuses should be inspected to ensure that they are not damaged or corroded. By following these best practices, we can ensure that the overcurrent protection system is reliable and effective in protecting the electrical system from overcurrent conditions. To further enhance our understanding of overcurrent protection, let's consider some common misconceptions and mistakes that can occur. One common misconception is that the overcurrent protective device is intended to protect the equipment connected to the circuit. While the overcurrent protective device does provide some protection for equipment, its primary purpose is to protect the conductors from overheating and damage. Equipment should be protected by separate overload protection devices, such as motor overload relays. Another common mistake is to oversize the overcurrent protective device. This can occur when the overcurrent protective device is selected based on the equipment's immersed current rather than the conductor's ampacity. Oversizing the overcurrent protective device can reduce the protection provided to the conductors and increase the risk of overheating and damage. Another mistake is to neglect the ampacity adjustment factors. As discussed earlier, ampacity adjustment factors are essential for ensuring that the conductors are adequately protected when multiple current-carrying conductors are installed in a raceway or cable. Neglecting these factors can lead to undersized conductors and an increased risk of overheating. Another mistake is to fail to properly coordinate the overcurrent protection system. Coordination refers to the process of selecting overcurrent protective devices that will selectively trip in response to a fault condition. Proper coordination ensures that only the overcurrent protective device closest to the fault will trip, minimizing the disruption to the electrical system. By avoiding these common misconceptions and mistakes, we can ensure that the overcurrent protection system is properly designed, installed, and maintained. In conclusion, overcurrent protection is a critical aspect of electrical safety. By understanding the principles of overcurrent protection, the requirements of the NEC, and the different types of overcurrent protective devices, we can ensure that electrical systems are adequately protected from overcurrent conditions. NEC Section 240.4b is a key provision that governs the overcurrent protection of conductors. It requires that the overcurrent protective device be sized based on the adjusted ampacity of the conductor, taking into account any applicable adjustment factors in the 80% rule. By following these requirements, we can ensure that conductors are adequately protected from overcurrent and that the electrical system operates safely and reliably. Remember to always consult the NEC and other applicable standards for specific requirements and guidance on overcurrent protection. This will help you to ensure that the overcurrent protection system is properly designed, installed, and maintained. Electrical safety is a shared responsibility, and it is essential to take the necessary precautions to protect ourselves and others from the hazards of electricity.